Okay, so in this video, we're going to do a quick intro to the two types of telescopes. So there's two main types of telescopes you need to know about. You need to know normal adjustment telescopes. So you can see it written in your test as normal adjustment, or you'll call it refracting telescopes, okay? Or you might see that you've got reflecting telescopes, or you might call them the Cassegrain telescope, okay? So if we're going to draw them, I'm going to switch to black because you'll be using a pencil. First thing I'm going to do is our principal axis, okay? So there's my principal axis. Okay, so it's our line that goes through the center of the lenses. This is a refracting telescope, so we know it involves lenses. A normal adjustment telescope means the distance between the two lenses is equal to the sum of their focal lengths. And it always is using convex lenses. So you're going to draw your two convex lenses. Remember, they're always going to be fatter in the middle. There's my two convex lenses. So again, two convex lenses. Principal axis is through the middle. We're currently going to draw a ray of light that comes through the center of the lens, and you're going to keep it going until it hits the eyepiece lens. Okay? What you're going to do then is you're going to mark on where your focal length is. And you have to remember, you can't do it in the middle. The focal length has to be closer towards the eyepiece lens. So there's the focal length of the eyepiece lens because it's a more stronger lens. The focal length is closer towards the lens, and the focal length of the objective lens. So there's F0, the distance between the focal point and my objective lens, and there's FE, the distance between the focal point and my eyepiece lens. And that's where you draw that your image is. And what you need to draw now is you're going to draw two more rays of light that are parallel to the first one, because these rays of light are coming from very far away. And when rays of light come from far away, they're always coming in parallel to each other. So these parallel rays of light are coming in towards each other, and they're all going to pass through the top of that image. Okay, so again, what we're doing is you have your three rays of light, they're all going to pass through the top of that image. Okay, sorry, that was a bad one. So we're going to do that again. So there again is the top of my image. It's not even touching my lane. And you got your ray of light. You have to make sure it refracts and goes through the top of the image, and your ray of light that refracts, and it's going to pass through the top of that image. Okay. Okay, now what to do is you draw a construction line. So a construction line you take from the tip of your image through the center of the eyepiece lens, and that's called your construction line. But you use a ruler, obviously. So construction line. Construction line is your reference line. What you want to do now is draw three rays of light that are parallel to that construction line. So three rays of light that are parallel to that construction line. And that's where your eye is. And your eye wants the rays of light to be parallel because it reduces the strain in your eye. Your head doesn't think light rays can bend, so it traces those rays of light back to where it thinks they came from, and that's where your image then is. Your image gets formed at infinity. So my image gets formed at infinity. Okay? The other type ones then is our reflecting telescope. So our reflecting telescopes, they are lenses, they are mirrors because they reflect things. Okay, so they're mirrors, they reflect things. And they used to be spherical in shape. What that means is when rays of light came in, what happens? They hit your mirror. So there's the back of the mirror. We know we draw our normal. The angle of incidence is equal to the angle of reflection. But what happened is when we did that, because they were spherical in shape, what happened is that when they hit your secondary convex mirror, they always had different focal points. So rays of light that are closer to the principal axis had a focal point that is further away from the lens. So what happened? We got spherical aberration. So to avoid this, what they did is they made parabolic reflecting telescopes. So that's why when you draw them, what you need to draw is you're going to draw a perfect parabola, and you use your rubber, and you're going to rub out a little hole in the middle where the light rays come out. But because I can't do that without rubbing out the whole line, because the way that it works with this pad, I'm going to draw it the way you shouldn't do it, and they can tell. But again, so there's where I'm going to drop my parabola and then open up again. But again, you can tell clearly that I lifted my pen. That's why you want to do it really smooth and then use rubber to rub out that little hole. I'm going to draw my principal axis that goes through the center. And again, what this is my mirror. It's my large, or my primary, so primary is first, my primary concave mirror. Okay, so what happens is I have my rays of light that come in, they hit the mirror. We draw our normal at 90 degrees the boundary, and you make sure that your angle of incidence is equal to your angle of reflection. So those rays are going to reflect. Make sure my angle of incidence is equal to my angle of reflection. They're going to reflect. And then they're going to hit a secondary convex mirror. So they're going to hit my convex mirror. And then what's going to happen is they have to cross each other at that opening in your mirror. So they're going to cross at the opening. Okay, so this is called your secondary convex mirror. Okay, so that's how you draw both of them. Okay, key things is when you're doing the mark schemes for these, when you're doing the refracting one, you have to have 3 rays of light coming in. But when you're doing the reflecting one, you'll need to have 2 rays of light coming in. Okay, they look for that. Okay, what this one is made of a reflecting telescope made of our mirrors. This one is our refracting telescopes made of our lenses. So because this one's of lenses, it does have both chromatic and spherical aberration. We can't avoid that. So that's why normally the reflecting telescopes are better. If you don't remember this is, just look back to our earlier video there when we went over what chromatic and spherical aberration was. Whereas reflecting telescopes, we can avoid spherical aberration by making them parabolic in shape. Okay. The other thing you know about when you're comparing telescopes is you look at the power is proportional to the diameter squared. So we're talking about the diameter of our telescope or our lens. So let's say that's our telescope, your collecting diameter, your diameter of your telescope or of your lens. The bigger we can make this diameter, the better the collecting power. Okay, so the better the collecting power, what that means is that we're collecting more light. If we're collecting more light, we're going to get brighter images. Okay, so we're going to get brighter images. Also, we're going to see further away. So we can see more distant objects, because before the distant objects were too far away, they were too dim to see. But because we now got a large diameter telescope, we got great collecting power, we can now see those really faint objects that are really far away. So we can see further away. And the last thing when you're comparing your telescopes is we look at the minimum angular resolution, which is roughly equal to whatever wavelength of light we're observing, divided by the diameter of that lens. So the larger the diameter is, clearly the smaller the minimum angular resolution is. The smaller the minimum angular resolution, so the smaller the minimum angular resolution, the better. Okay, so what that means is, let's say there's 2 stars that are really close together. If I have a telescope that's got a small diameter and it's got a poor minimum angular resolution, it's not able to see between those points that are close together. Instead of seeing them as 2 separate stars, it'll just see them as one big blur. So I don't really know what's there. I just know it's a big blur of light. So it could be one really big star, or I don't really know what's happening. But if I have a larger diameter telescope, what we can see then is because it's going to have a better minimum angular resolution, I can now see that blob a lot better. I can see it's actually 2 separate stars. So minimum angular resolution, it tells about the resolving power. Okay, it tells about the resolving power of the telescope, about the ability to see 2 separate points that are close together as 2 separate points. Okay, and there's another definition then that applies the Rayleigh criteria. And the Rayleigh criteria is when we say that when you look at the pattern of the light, you want to always make sure that the central maximum of the second image always coincides with the minimum of the first image. And that's the only way that we're going to resolve it. So again, when that central maximum of the second image coincides with the first minimum of that first image. Okay, and there's some of that notes in that on the reading. Okay, so again, to compare telescopes, always talk about whether they have chromatic or spherical aberration. Look at their power and look at their minimum angular resolution.